Swayam Prabha. Digital India. Educated India.
Now we proceed to one of the advanced abrasive machining process, that is called electrical discharge grinding and electric discharge diamond grinding process. This particular process is a hybrid version of electric discharge machining process. Okay. So, to go into this particular lecture, we will see what all we are going to see. Those are nothing but introduction to electric discharge machining. First of all, we should know what is electrical discharge machining. Many people you might know already, but some of the people who are new to electric discharge machining and other things, I will explain you what is electric discharge machining and material removal mechanism. Many of you may be well acquainted with material removal mechanism overview, but how internally the in an explanatory manner how the material removal mechanism takes place in electric discharge machining, I will explain to you. Then we proceed to the hybrid processes, that is called electric discharge grinding, then electric discharge diamond grinding, then the material removal mechanism in electric discharge grinding, dressing, declogging of chips from the grinding wheel in electric discharge grinding process. What I want to specify in this particular slide is, since this particular process is an abrasive oriented process, so we deal mostly about electric discharge diamond grinding process rather than electric discharge grinding process. Okay. Why EDDG is important rather than EDG, that you will come across whenever I am teaching the course, because in EDG mostly you may not use the abrasive particles on the grinding wheel, but in electric discharge diamond grinding process you will use the diamond abrasives on the metallic bonded abrasive wheel. Okay, that is the difference. In the electric discharge diamond grinding, you will have the abrasive particles on the wheel. In electric discharge grinding, sometimes or the most of the times you will have only the metallic wheel, there won't be abrasive particles. Since this particular course deals with abrasive oriented process, so we deal mostly in EDDG process. So, who and how EDM is invented? So, the Lagrange brothers found that the female and male parts of an electric switch have craters formed on it. So, what will happen? So, whenever you see most of the in commonly houses, if you see the electric connections or the switches where you have male and female part, because of which if there is a loose connection or the connection is not proper, there will be a spark, and the spark will lead to erosion of the material. Okay. This was observed by Lagrange brothers and they invented the electric discharge machinings. Okay. So, previously what they have done is they have patented it with a name called electrospark machining machine, later it is named as electric discharge machine. Okay. So, they have patented it and this is how the people invented this particular process. Like Isaac Newton invented the gravity when the apple fall on his head. Similarly, these people also observed the natural phenomena and they have invented this particular process. If you see electric discharge machining, normally you have die sinking EDM, then you can do by EDM drilling and die sinking EDM and other things. Cutting, slicing you can do by a rotating disc, that is called electric discharge grinding also you can say. Slicing done by the ribbon blade and other thing, slicing, cutting done by the EDM. Then the grinding process you can do the slicing by EDM with a a ribbon or a blade, cutting by the EDM with a wire and other things. These are the some of the varieties that you can do, and this shows the classification how you can do the electric discharge machining. So, the electric discharge machining process, if you see here, what will happen is, this is the overview, and I am going to tell you how the material removal mechanism will takes place. And if you see this particular area is zoomed up here. Okay. So, the tool is given negative terminal and the positive terminal is given to workpiece, and you can see here some of the things are ions, some of the things are electrons. How these are all will flow and the material removal mechanism will takes place, we will see here. What is here it is going to happen is, assume that I have a negative terminal here and the workpiece is positive terminal. Okay. Connection is provided. So, dielectric fluid is there and other things are there. Okay. So, when the electrons moves from here, normally some of the books, for simplicity sake and other things, what they explain is, you have a negative terminal, you have positive terminal, and because of the dielectric fluid present in between, there will be a potential difference. If there is a potential difference, the spark will occur. So, the spark will occur. This type of mechanism is explained by some of the books for the simplicity purpose. Now, the question is how the spark is generating. That is most important to understand from the point of physics. Okay. Dielectric fluid will have dielectric strength, okay, below which what will happen, it will act as an insulator, above which it will act as a conductor. Okay. So, assume that our dielectric fluid is a deionized water. Okay. There are many varieties of dielectric fluids. Let me consider this is a deionized water, deionized water. Okay. What do you mean by deionized water? Dehydration means water is gone out of the body. Similarly, deionized water means the ions are mostly removed. You cannot remove all the ions, but it is reduced in ions number. Okay. So, whenever you give the negative terminal to the tool and positive terminal to the workpiece, what will happen? Electrons start flowing from this particular side, and these electrons, where it will go? These electrons will hit one molecule of deionized water. When it hits one molecule of deionized water, so what will happen? It will release lot of electrons, and since it is a deionized water, ions are very less, and it also develops some of the ions, and ions move towards negative terminal and electrons start moving towards positive terminal. Okay. So, these electrons will go and hit the next set of deionized water, that is called dielectric fluid, and generate. So on it will generate, and millions and millions of electrons will move towards the workpiece, that is the positive terminal, and the kinetic energy of all these electrons will convert into the thermal energy. That is why there will be a spark, and this spark will remove the material by melting and evaporation. Okay. That is how the spark will generate. It is not that if there is a potential difference, then the spark will generate. It is the kinetic energy of millions and millions of electrons that are generated by the dielectric fluid because of few electrons that are coming from the negative terminal, and this kinetic energy converts into the thermal energy, and this thermal energy is concentrated on a specifically one zone where the distance is very less. That means that inter-electrode gap is very less. Normally, if you see R is equal to rho L by A, that means L specifies inter-electrode gap. Okay. Wherever the inter-electrode gap is very minimal, there that particular position only the melting and evaporation takes place for that particular moment. Okay. That is how you will see the spark on the positive terminal or the workpiece. Okay. The channel that is formed here is a ionization channel. Okay. Normally some of the books they will explain like a ionization channel, where you can see the some of the ions that are moving towards the negative terminal and electrons are causing the thermal energy on the workpiece, so that melting and evaporation will take place. Okay. That is how the mechanism works in the electric discharge machining, and you hope you understood how the spark is generated. It is not because of the potential difference directly spark will not takes place. Because of the potential difference, electrons that are there on the negative terminal try to move towards the positive terminal, but in between there is a dielectric fluid is there. This dielectric fluid molecules are interacted by the electrons that are coming from the negative terminal, and thus this one molecule of dielectric fluid will dissociate into many of electrons and few of ions. At the same time, you should note that electrons are much smaller compared to ions. At the same time, your workpiece is below. So, the gravity also will help. At the same time, the electrons being a smaller size, it will move with a higher velocity and hits. If the kinetic energy is very high, half mv square, velocity is very high, that means that kinetic energy is very high. If the kinetic energy is very high, obviously the material removal will be very high. Okay. So, that is how the kinetic energy converts into thermal energy, and there you will see the spark. Okay. That spark will generate lot of heat, and that heat will makes the workpiece material to melt and evaporate. Okay. At the same time, this molten metal will be carried away by the dielectric fluid that is flowing across the two terminals. Same thing will also happen on the other side, like ions also go on the opposite direction and hit the tool, but being a higher size against the gravity and being the number of ions are less, so the tool wear will be always less compared to the workpiece material removal. If you see here, this is ionization channel formed and the melting and evaporation takes place and the material is removed. You see the material, how much material is removed on the workpiece, and at the same time there is some area is affected on the tool also. That is why the material removal on the workpiece is higher compared to the material removal on the tool. Okay. So, spark in EDM, that is how the spark, as I said, there will be a negative terminal and positive terminal, electrons moves and the material removal takes place because of the spark that is generated when the electrons hits the workpiece, and indirectly what you are going to get is replica of the tool. Assume that your tool is like this, you are going to get the converse shape of this one. Okay. So, you will get a converse shape because the effect is rho L by A, wherever the L is minimum, there the concentration of these electrons will be more, that means that kinetic energy will be more, and that particular portion the spark will generate and material will remove. So, if this is the original material and because the distance is less here, so the material will remove more in this one, so that you can get a replica of the cutting tool. So, there are two polarities, one is the normal polarity and reverse polarity. So, normal polarity, normally tool will be given negative terminal, positive terminal will be given to the workpiece. In the reverse polarity, some of the people they do the literature, some of the people do the research on reverse polarity for electric discharge coating and other things. People will say in that circumstances people will use negative terminal to the workpiece and positive terminal to the tool. Okay. So, the voltage and current, if you see the voltage and current, there will be a like duty cycle and other things. Normally there will be a ignition delay, there will be sparking will takes place and other things. Starting point to the starting point of this one normally is called one duty cycle. Duty cycle comprises of two segments, one is the sparking region and non-sparking region, or where the voltage will be applied and where the voltage will be 0. Okay. This whenever the duty cycle is on, the sparking will takes place. Okay. That is how the material removal will takes place. So, the distribution of spark energy, normally it will be conducted away by the workpiece, stored in the workpiece as well as used for the erosion. Normally, if you are using mostly used for the erosion, that means that material removal will increase. In the tool, the sparking energy always conducted away. Basically, the tools are like copper, brass, any conductive materials will be used. Some of the things will be stored, at the same time some will be used for the unwanted wear. So, if you are going to use tungsten carbide type of tool and other things where the melting point is very high, the unwanted wear will be minimal. So, dielectric fluid, it will conduct away, it will take away the energy and it will store inside. Debris, normally it will be stored, and residual, normally some of the spark energy goes by radiation, ionization channel formation, as a light and as a sound. Whenever you do the EDM process, you will see the some sparking and the sparking sound and the other things. Okay. Dielectric system, it consists of dielectric fluid, reservoir, filters, pumps and delivery devices. Normally you require filters because the debris will be a big problem. If you do not have filters, the debris will recirculate in the process. A good dielectric fluid should have the following properties. It should have high dielectric strength, that means that remain electrically non-conductive until the required breakdown voltage is applied across the electrodes. Okay. Take minimum possible time to break down, that means ignition delay will be very less. That is what we have seen in the previous slide also. Deionize the gap immediately after the spark is occurred, serve as an effective cooling system because melting and evaporation takes place and the dielectric fluid has to flow. So, this dielectric fluid should cool the tool at the same time, otherwise if it is continuously heating up, the tool also will wear out. At the same time, this cooling, what will happen, the molten metal will be carried away in the form of spheroids and other things. That is why whenever you see the EDM surface in a surface morphology of an EDM surface, if you see what will happen, if you can see the some of the spheroids on the recast layers. This recast layer, heat affected zone and other things we will come across in the upcoming slides have high degree of fluidity. That means that the viscosity should be low. If the viscosity is low, what will happen? It can move to each nook and corner of the complex geometry that tool possesses and which you want to replicate on the workpiece. The commonly used dielectric fluids are the transformer oils, paraffin oils, kerosene also people can use, lubricating oils, and mostly people will use deionized water. So, here one of the research point that I want to tell you is you can use paraffin oil which is a carbon based, at the same time deionized water. If the people want to do the finishing operation followed by the EDM process, normally you should prefer deionized water, because if you are going to use paraffin based, what will be happening here is, if the paraffin is there, the carbon will be there. So, the surface will form carbides. Carbides are much harder and your polishing work or a finishing work will not remove these carbide layers. If you are going to use deionized water, in that circumstances, what is you are going to get benefit is, it will form the oxide layers, and oxides are easy to remove by the polishing or the finishing action. That is why whenever, if at all people want to do for machining using electric discharge machining followed by some polishing operation on that particular surface or hole or any other geometry, you are recommended to use the oxide based fluids rather than carbon based fluids. So, the dielectric system, deionized water is the better one, that is what I said. At the same time, the advantage is it gives higher MRR, more effective cooling system, Disadvantage is it also will have high tool wear rate and causes the corrosion, that is what I said, no, oxide film form. So, if at all your requirement is to finish, then this corrosion will goes off. Okay. To overcome this problem, inhibitors are used, electrically conductive increase for an acceptable level, used for Wire-EDM drilling of small holes and the thing. As I said, filtration of this dielectric fluid before the recirculation to maintain the fixed dielectric strength. That means that if you are going to use directly without the filtration system, the debris particles will be there, and these debris particles are conductive because your workpiece and tool both are the conductive materials, and if these debris or spheroids come in between, if this comes along with the dielectric fluid between the two electrodes, that is positive terminal and the negative terminal, what will happen is the strength or the dielectric strength of the dielectric fluid will reduce. So, if it reduces, then there will be different mechanism. Some of the people are studying about this powder mixed EDM and other things. People use conductive, people use the ceramic, and many abrasive particles also people are using. So, you can go through it. So, some of the people who are interested in using the powder mixed EDM and other things, you are most welcome, and you can use for the proper cause. The effect of current and frequency, if you see the effect of current, in the current, if you are going to increase 1 ampere to 4 ampere, for example, what is happening is your sparking strength will be very high and the sparking size will increase high. If your sparking size will increase, what will happen here is your crater size formation. If you see here in the, this is the crater size formation with 1 ampere, and if you see 4 ampere, the crater size formation is very high. That means that if at all I want the material to be removed, what you have to do is you have to go for more and more current rather than less current. Okay. If you want to use for the better surface finish, assume that you want to use one condition for material removal application, then you have to obviously go for higher currents. If you are going for the finishing applications, then you have to go for less current. Why I am saying is, in this condition your surface roughness will be like this. So, the surface roughness is very high in higher currents and surface roughness will be very low in low currents. At the same time, if you see the frequency of sparking, if at all, if you see the frequency of sparking effect on the surface, if at all you want to remove more and more material, then you have to go for high current along with high frequency. Okay. So, this combination will give you better MRR. Okay. At the same time, if at all you want to go for better surface finish, at the same time at the faster rates, then you can go for this particular combination, 1 ampere with high frequency. Okay. So, as I said, the debris formation and other things. So, what you are going to see around the micro hole or the hole that developed using EDM process is, this is my diametrical hole. Across it, what is happening here? I said melting and evaporation. Okay. So, if there is a melting and evaporation, if there is a spark because of the kinetic energy that is converting into thermal energy, melting and evaporation. If there is a evaporation, well and good. If there is a melting, what will happen? The dielectric fluid's responsibility is to carry this molten material, and the dielectric fluid may not carry all the molten material. Some of the molten material will cool down there, because one of the main functions of your dielectric fluid is to cool the interelectrode gap. That means that it has to cool the workpiece, it has to cool the tool also. Okay. In that circumstances, what is happening here is the molten material which is unable to flush by the dielectric fluid will cool down. That means it is forming a layer, that is called a recast layer. What do you mean by casting? Casting means you have a molten metal, you have cope and drag pattern, then just pour it and you solidify it. Okay. Then you are going to get, that is called casting. Here melting taking place, but unable to goes off because of the dielectric fluid cooling effect, it is solidifying. That is why recast layer. So, it is recasting on a, assume that the workpiece is casted previously on which you want to do the EDM process. It is molten metal unable to goes out. So, it is casted again around the hole, that is nothing but recasting taking place. That is why it is named as a recast layer. Because in the recast layer the temperature is so high, that is developed because of the kinetic energy of the electrons which is converted into thermal energy, the grain structure will be very high. Okay. So, if you see the next layer, that is called heat affected zone, because of the heat that is generated during the hole generation or drilling the hole by EDM process, the molten metal which is unable to go, that is the recast layer, experiences the maximum temperature, because you have seen the workpiece carries by the conduction action. Okay. So, by the conduction action heat carries. So, this heat carries, what will happen, there is a grain structure slightly lesser than that one, that is called heat affected zone. You can see here, this is called the heat affected zone, this is recast layer. In the heat affected zone also, what will happen is you are going to see the constant grain structure which is starting from the recast layer and the last layer where it has its own size. And heat affected zone also will have some size which is less than the recast layer. And the conversion layer means the layer or the converted layer, that means that heat affected zone have their own microstructure which is bigger size compared to the parent material microstructure. So, the microstructure changing from the heat affected zone to the parent material, gradual change of the microstructure or the size is nothing but the converted layer. That means that conversion of heat affected zone grain size to the parent grain size, that conversion thickness is nothing but the converted layer. These are the three layers that if at all you want, you can Google it and you can see these layers microstructure, how it will change. So, now we move on to the hybrid version, that is called electric discharge grinding. In the electric discharge grinding can be classified into conventional grinding, hybrid grinding. Hybrid grinding we have many things, but in the particular class we are going to see about electric discharge grinding and electric discharge diamond grinding process. So, what are the basic industrial problems? This normally diamond grinding, which is a limitation, basically problem is high cost and the high specific material removal energy is required, that means the specific energy is high. Strength degradation, because whenever you want to do the polishing of this one using mechanical methods, what will happen is the strength may go down and the wheel wear will be a high and big problem, and the dressing problems also will be there in this particular process. That is why you can incorporate the positives of EDM. However, the problem with EDM is low material removal efficiency, at the same time resolidified and white layer intensified micro cracks, because this grinding of this diamond and other things, what will happen is it will induce the micro cracks. Normally in a ceramic materials, diamond, CBN and cermets, these are all some of the ceramic, silicon carbide, alumina, these are ceramic materials. The basic problem with the ceramic materials is these are not very good at conducting the heat. What will happen on one edge, assume that this is my abrasive particle, if temperature is high here, point A, so it is a bad conductor, point B, it will be at room temperature, there will be a problem of, because of the temperature difference, there will be a problem of cracking. So, that is the biggest problem in the ceramics. So, that is why ceramics machining is one of the biggest challenges that normally manufacturing engineers faces. Okay. Grinding of hard material, if you see what is a high normal forces will be there. Okay. So, that is why you have to reduce the forces. So, rapid formation of the wheel flat, that means that the glazing of the wheel will takes place early, and the wheel clogging, the abrasive particles adjacent to the abrasive particles clogging will be occurred, and inefficient mechanical dressing. Okay. So, mechanical dressing may not work. Okay. If at all I want to go for hard materials grinding process, these are the biggest challenges. How to overcome? You can overcome by electric discharge diamond grinding process. So, how we can overcome that, we will see in the upcoming slides. So, what will happen if you are going to add EDM process to the grinding process? What will happen here is the EDM in this particular wheel normally will be made up of metallic, which is electrical conductive material. So, that what will happen, the sparks will be generated between wheel material, which is a bonding material, to the workpiece material, because of which what will happening is there is a spark will be generated, and the spark will melt the workpiece material. Okay. If it is melts, what will happen is the thermal softening of the workpiece material will takes place, and it is easy to remove the material by grinding action. That is what we are going to see. If the thermal softening will occur, what will happen? Reduction in forces will occur, better accuracy will be there, and better surface integrity will be also there. In process dressing, basically more efficient than the mechanical dressing and no loss of machining time. Normally what will happen, if there is a spark generation, as I said, ions also move towards the negative terminal. Then what will happen, if there is a chip on the grinding wheel, that will melt and goes off. So, there is no requirement of dressing additionally in this particular process. That is why there will not be any clogging. So, declogging will be done automatically in the electric discharge diamond grinding process. No slide contact between the bond and work, and the comparison with ECG, there will be another one where I will introduce to you electrochemical grinding if time permits. So, no sludge disposal problem, because in electrochemical grinding process the problem is your fluid is a chemical, that here you are using a dielectric fluid which is a deionized water, there will not be much problem in disposing it. But here in electrochemical grinding the chemical has to be disposed, which is already having the debris. So, it will be very difficult. So, material removal mostly due to by the abrasion action in electric discharge diamond grinding. If you see electric discharge grinding in particular, here there is no abrasive particles are used and only rotation of the disc is taken place. If you are going to see here, the servo controls are there and insulating material and other things are there. So, that there will not be any problem of conduction and other things. You have only the disc. This is the disc where there is no abrasive particles and the workpiece material. Here you are rotating the disc, which is a metallic disc, against the workpiece, and you are flushing the along with the dielectric fluid. What you are going to get is the temperature generation because of the sparking, that is came into existence because of the kinetic energy of the electrons, will gives the molten material and sometimes it evaporates because of the kinetic energy of this grinding wheel. So, the flushing will be good and the material removal mechanism will be good. Okay. The same thing you can see here. So, the negative and positive terminals are given to the wheel and the workpiece respectively, and the dielectric fluid is there and you can remove the material. But please note that there will not be any abrasive particles in this particular research work that is done by Professor Koshi and Professor Jain and Professor G. Kelar. So, there will be a spark, how the material will be removed, there will be a spark like EDM and the material will be removed. So, what is the difference between original EDM, that is die sinking EDM, and this particular EDG? You have a grinding disc because of the conductivity of the disc, which is made up of copper or brass or stainless steel or any conductive material. what is going to happen is, because of this rotation, the flushing will be very good and melting and evaporation obviously will be taken care by the EDM mechanism. So, the material removal is good, but the big problem here is to remove the material removal further. What the people have done is they have gone for electric discharge diamond grinding process. Now, we move to electric discharge diamond grinding. In short, it is called as EDDG. So, in electric discharge diamond grinding process, it is a mixture of or the combination of grinding process and electric discharge machining, and wherein you will use metal bonded wheel. As we have seen in the grinding wheel specification, we have vitrified bond, resonoid bond, shell-lock bond, metallic bond and other things. Metallic bond specified by M basically. Okay. So, metallic bond, as if you see the metal having the good conductivity, whenever you are using this particular wheel in terms of electric discharge diamond grinding process, you should have the tool and workpiece both are conductive in nature. For that purpose, you will use the metal bonded wheel, wherein you brace or you can mix the abrasive particles on it. If you are using the diamond particles, then it is called as electric discharge diamond grinding process. Conducting of the workpiece material is mandatory, that is why you are going for the metal. In process and continuous dressing and declogging will takes place in this one. How it will takes place, we will see the mechanism and other things. Reduction of the grinding forces, because the electric discharge machining process makes or gives some sparks on the workpiece surface. If you are going to give the sparks, what will happen? The thermal softening of the workpiece takes place. If the thermal softening of the workpiece takes place, then the workpiece material experiences very less forces from the abrasive particles in order to shear out the workpiece material. So, if you see here in this particular, this is the schematic view of electric discharge diamond grinding process, wherein you are the wheel as well as the workpiece both are inside the dielectric fluid. That means that dielectric fluid chamber is there, wherein the dielectric fluid is filled, and you have the abrasive particles which are in contact with the workpiece, and there will be a spark that is generated which makes the workpiece softer. Then the abrasion action of the abrasive will takes place and it will shear off the workpiece material. So, it is a combination, as I said, the electric discharge machining and at the same time grinding process. That is why this particular process is called as a hybrid process, where two mechanisms or two individual physics is merged here in this particular process. So, electric discharge diamond grinding process, what I was speaking to you, if you take the particular wheel will have lot of abrasive particles. If you take a one individual abrasive particle, if it looks like this, you see this is the metallic bonding is there. As you have seen, the grade says that how strongly the bonding material, that is the metal bonding material, is held the abrasive particle, that is decides the grade. Okay, this particular bonding, whatever I am giving the lines, this particular bonding will use the grade of the grinding wheel. Okay. So, what is happening here? My shearing action is taking in this direction. Okay. So, there is a spark. As you know, the spark, when the electrons are moving from the negative terminal to positive terminal, in between it come across the dielectric fluid. Dielectric fluid is assumed that it is a deionized water, it will gives lot of electrons. These electrons goes and hit again the dielectric molecules, which again gives millions and millions of electrons, and which goes and hits the workpiece. Because if the workpiece is hits like this, there will be a spark, and this spark generate the melting and evaporation. And if at all you do not want evaporation, you can go for low current and other things, so that you will have only melting. And because of the thermal conductivity of the workpiece, what will happen? This thermal conductivity pass on into the workpiece material. Okay. So, this thermal conductivity, because of the high thermal conductivity at this position, it will move towards other also. So, the thermal softening of the workpiece takes place. Here it is a molten state, this is molten, and if you see here, this particular portion will be like a hot portion, that means that it is in a semi solid to solid motion, it is in a semi solid to solid shape, it is in a semi solid to solid state, okay, semi solid to solid state, okay. That is why thermal softening of this hard material will takes place, and the abrasion action of this abrasive will takes away this intermediate or the thermally softened layers of this particular material, and thus the forces required for shearing of this particular material will decrease. You can see here, so how the material and other things are happening. If you see the same mechanism here, what is happening here is the spark is taking place. If the spark is taking place, this particular material will become melt and the thermal conductivity will pass on to this particular section, and this particular section what will happen, become the thermally softened. So, the force required to shearing force and the indentation radial force, both are less compared to the grinding process. What I mean to say here is, if you are taking a grinding process and if you are taking electric discharge diamond grinding process, in this one the forces requirement FR1, FS1, FR2, FS2, what I mean to say is your FR1 will be greater than FR2, FS1 greater than FS2. That means that for the same workpiece and tool materials, that means that grinding wheel, even though you are using a vitrified bond along with the diamond particles, if you are going to experience the radial forces and the shear forces in this way, if you are going for electric discharge diamond grinding process, thermal softening action will be dominating, because of which your both the forces, shearing as well as the radial forces, will be lower compared to your normal grinding process. That is what the comparison. If you see the basic configurations of electric discharge diamond grinding process, you can directly, if you see 1, 2 and 3 specifies the grinding wheel, workpiece and power supply. So, normally you can supply directly to the workpiece itself and the grinding wheel, or you can also give to certain electrodes and you can go for the workpiece. These are the two configuration 1 and configuration 2. These are the basic configuration that if at all you want more details, you can proceed to the Professor Koshi's paper and you can understand more and more about this particular electric discharge diamond grinding and its basic configurations, and the paper details are given here at the bottom of this slide. So, if you see the diamond grinding setup, normally the setup will be like this, and the dielectric fluid is fed, at the same time the workpiece will be there inside. This is how your grinding process looks like. Okay. Whatever you have seen the previous one, that is the machining region only of the electric discharge diamond grinding process. In this one you can see the overview, where you can give the negative terminal and positive terminal. Normally negative terminal you are going to give to the grinding wheel, and the positive terminal you are going to give the workpiece, and you have to make sure that in the spindle it should be normally insulated, so that it won't conduct the negative terminal to the complete machine and other things. That is the precautionary statement, and if at all you are going to do certain experiments on this one, be cautious about insulation to the complete setup from the grinding wheel. Okay. Input variables, normally workpiece materials like HSS, cemented carbide, and the parameter will be wheel speed, current, how much current you are going to give, and the pulse on time and pulse off time and all those things. If you are controlling the pulse on time, automatically pulse on time and pulse off time, which is called as a duty cycle, will be varied. Okay. So the responses, normally this particular processes will be basically used for material removal applications of very hard materials. You can also measure the forces using dynamometers like normal force, tangential force. As I said in the previous slide, it is a radial force also. People can call in many ways. This itself you can call radial force, and this also called shearing force or shear force. Okay. So metal bonded, normally alumina wheel is economic. So what I mean to say from this particular statement is, if you are not having the diamonds normally will cost much higher cost. So you can go for metallic bonding along with the alumina oxide. Okay. Aluminum oxide abrasive particle, that means that alumina Al2O3 particles you can go, and this can be a economic viable solution if at all you want to go for this particular process. So material removal, if you see the material removal, as the wheel speed increases, the MRR gradually increases in the all current. If you see zero current, that means that there is no removal of material using the erosion techniques, the spark technique. If you are going to increase the current, what is going to happen here is the material removal gradually increases. Why the material removal is less? If you see at 0 amperes, what is happening? It is purely the grinding process, because there is no sparking, there is no melting and evaporation. For the same material and tool combination, that means the material as well as the grinding wheel combination, you do not have the sparking here because your current is less, that is DC power supply you are going to switch off for this particular experiment. Since there is no sparking, there is no melting and evaporation, because of which the workpiece hardness, original hardness plays a major role, and you cannot remove much material, and you may observe very fast glazing, because normally this EDDG application is for harder materials, and diamond particles is also harder at the grade, that means that your metallic bonding is also will be like grade will be hard grade. Okay, it is not soft. In that circumstances, you may experience the glazing, that means that your abrasive particles goes off. Okay. So you should be very careful, that is why the material removal is less. As you see, for 1 ampere, that means that you are giving very less amount of current. So reduction of MRR at higher end of the wheel speed is due to wear and flat formation, that is nothing but the you are appearing the glazing, and at the same time introduction of the current in the spark gap improves the MRR in all. That means that as you increase, what is going to takes place is your sparking will be improved, at the same time your melting and evaporation will be improved, and most of the material you can remove by the two actions, what is melting and evaporation as well as your abrasion action. Okay. In all the conditions abrasion is constant, however melting and evaporation will vary and it will increase in this direction. Okay. If your melting and evaporation increases in this direction, so your material removal rate obviously increases. So if you see the gap current versus normal force, so if you are going to increase the gap current, the thermal softening effect, normally high current, if you see use higher softening and lower normal forces. That means that if you are observing the forces, what is our requirement? Basically transforming from the grinding operation to the electric discharge diamond grinding operation. Our requirement is, if at all we get a hard materials to be machined, assume that I am going to get a workpiece material as HSS, high speed steel, which is normally considered as a tool material for the mild steel and other steels in a lathe process. Assume that I want to do the machining on top of it. What will be, if you are going to use for the normal grinding process, you are going to experience enormous forces. If your forces are very high, then the abrasive particles goes off. So you, in order to counter it, you are going for electric discharge diamond grinding process, where you incorporate the EDM process, that is called electric discharge electric discharge machining, where the sparking will takes place and the thermal softening of the workpiece material will takes place. If you see the current increment, as we have seen in the previous also and in the previous slide in electric discharge machining basics, if you have seen, if the current is increasing, the amount of material or the spark size will increase. If the spark size increases, what will happen? The crater bigger and larger craters will form. If the larger craters are formed, what will happen? The thermal conductivity will goes to larger areas and you can remove the material easily. For that purpose, if you see, the thermal softening will increase if you are going to increase the current. That is the basic thing. If you are going to increase the current, what is going to happen is thermal softening will takes place. That is written in the bottom. The thermal softening will takes place. If the thermal softening will takes place, what will happen? The interaction forces between the grinding wheel, at the same time the workpiece will decrease gradually. That is what the graph shows. If you are going to increase the speed of the grinding wheel, sufficient time will not be there to melt and evaporate. So, the forces are slightly higher, okay, for the same current. If you see here, these are the surface morphology. Normally, if you are going to use the 0 ampere, that means that it is pure grinding. If you are going to use very less current, very high current, if you see the difference between figure 1, figure A and figure C, you can clearly see that in the figure A only grinding marks are there. This is the predominant direction of surface roughness, that is called lay is a straight line. If you see here, craters are there, at the same time there are the scratch marks are there. This is the combination of the material removal is by the melting and evaporation as well as the shearing by the abrasive marks. That's why the material removal will be more in case of figure C compared to figure, where you are going to put the current as well as abrasion action. So, dislodging, if as I said, whenever you are giving certain input conditions like depth of cut and other things, what will happen is, when you will have always some chips will come and clog around the abrasive particle, okay. There will be a gap between two abrasive particles. Normally in open structure, you have studied about the grinding wheel specification, where there is a open structure and the closed structure. In open structure, the distance between two abrasive particles normally will be high compared to the closed structure. In that way, what will happen in the open structure, the chips will come here, and your EDM process, how the EDM process will work, there will be a spark because of the electrons and other things, okay. This spark not only removes the material from the workpiece, it also removes certain material from the tool also. In that way, if what is the material that will come in contact, the chips will come in contact before the wheel bonding material. That is why it will declog the material, that is a chip material from the grinding wheel. That is why declogging, and it is also known as the dressing operation. You do not require a diamond tool holding like this and rotating the grinding wheel in normal conventional process, because here whatever the ions that are there generating during the electrons bombardment with respect to the dielectric molecules, the ions also will generate, and the ions will try to move towards the grinding wheel, and this will bombard on the clogged material, and melting and evaporation takes place there also, because of which declogging will takes place indirectly. Dressing is inbuilt process in this one. So, there is no requirement of dressing in this particular process additionally. So, the conclusions: electric discharge grinding technology is alternative for grinding electrically conductive and hard materials. Basically, it will be basically uses for hard materials. Improved grinding performance due to continuous dressing, because the dressing action and declogging action will be taking place continuously. This process is essential for economic viability and possibility of the hard material with aluminum oxide will be economic. Instead of going for diamond particles, you can go for alumina particles. Then this electric discharge diamond grinding, the name will change to abrasive electric discharge grinding process, Wherever you can use silicon carbide or alumina or boron carbide or cerium oxide, whatever the abrasives you use, instead of diamond word will change, that is all. We move on to another process which is called as abrasive wire electric discharge grinding process. This is also similar to the previous process, that is called electric discharge diamond grinding process, wherein, as I said, you can go for alumina and other things. That is why the word came at the start. So, that means abrasive wire electric discharge grinding process. Okay. So, before that we will just see the wire electric discharge machining process. This is the commercially available wire electric discharge machining process. You can see a wire here. This wire will continuously rolling, or it will be continuously moving by the spools, and the material will be removed. The material removal action will be taken care by the electric discharge machining process mechanism only. Here what will happen, there will be a wire which is a conducting material, workpiece also a conducting material. Wire is negative terminal as well as the workpiece is positive terminal, and the dielectric fluid is fed here. If you see here, dielectric fluid is fed. So, the mechanism of material removal will be same. So, there will be a negative terminal, there will be a positive terminal, and the material removal takes place by virtue of electrons bombardment on the workpiece, and kinetic energy of the electrons will convert into the thermal energy. So, the melting and evaporation takes place. The beauty of this Wire-EDM process is that you can make the complex shapes, but thickness wise it has some constraints. If you have minimum 5 mm, 10 mm thicknesses, so you can cut the complex shapes using Wire-EDM process. So, if you want to have the tool life, that is a wire life, normally you will go for some of the advanced wires, that is called stratified wire, wherein your core is made up of copper, that means that one metal, and outside will be made up of another metal where is a zinc alloy which is low melting point. Basically this is a high, this is expensive, at the same time you cannot use the recycled because this wear out will takes place. Normally the stray currents and others can be avoided by this particular advanced wires. Okay. So, hybrid abrasive machining process, normally hybrid, as I said, some of the people might have not got the concept of hybrid. There is slightly difference between advanced and hybrid. So, hybrid machining process, material removal due to more than or equal to 2 ways. That means that you will have combination of 2. Okay. A portable TV in olden days, nowadays LCD, LED, this is the advancement of TV. Okay. But the mechanism or some of the technologies are different, but the thing is that it is an advancement. But if at all you are going for hybridization, you have to hybridize. So, 2 mechanisms. So, why it is required? The hybridization, normally one process will have its own advantages and disadvantages, another process also will have advantages and disadvantages. If at all I want to have the advantages of both 2 processes, then you have to combine both 2 processes, that is called hybridization. At present, many materials cannot be machined to the satisfaction level due to technological limitations or sustained crack while the machining. This like formation of recast layer and other things. For that purpose, abrasive Wire-EDGs came into picture. The spark creates the positive ions and electrons. Electrons impact on the workpiece material and material removal due to melting and evaporation. Then abrasion action of the abrasive particles also will take place. That means that you have a Wire-EDM process plus grinding process. That is what is the advantage. If you see here, this is how it also looks like a Wire-EDM process only, but the thing is that here the wire is having the abrasive particles. The current voltages are main important parameters here. At the same time, machine gap is also important factor which you can play in this particular process. It is similar to Wire-EDM process, but abrasive Wire-EDG is another variant. Grinding and Wire-EDM is combination which is called as a hybrid process. If you see here, the mechanism of material removal is same as the previous process, but only thing is that here instead of a wheel, what you have seen in the previous process, here it is a wire. Okay, rest of the mechanism is approximately same. So because of the metallic wire which possesses the abrasive particles, metallic wire will have the spark which makes my metal thermally softened, and the abrasive action of the abrasive particles will takes place. Okay, that is how it is the same explained in a close up view. This process combines the principle of wire-EDM and abrasion. Non-conducting abrasive particles are fixed on the wire. That means that it will have the 2D abrasion or the two body abrasion. The material removal due to spark erosion and abrasion, that is called here. What is you are going to see here is erosion. This is called the spark erosion and this is called abrasion. Okay. So because of these two actions, material is removed. Okay. So the people who have not understood, or if you are not there in the few minutes back, mechanism is clearly explained here. Because of the spark erosion in this area, what will happen? Thermal melting and evaporation takes place. Not only melting and evaporation takes place, this also conducts the lot of heat inside. Okay. Because of which what will happen? The thermal softening of the workpiece will takes place, and the abrasion action of the grinding wheel or the abrasive wire will remove with very less normal forces. Okay. That is the beauty about this process. That is why the material removal also will be very high if you are going to increase the current. At the same time, if you are going to increase the current, the normal forces will be very less. Okay. This particular picture will clearly give you what you have studied in the previous graphs few slides back. Abrasive wire, basically it is a high tensile strength normally. If you see the abrasive wire how it look like, normally it should have high tensile strength, because now this will have a carbide rollers with V shaped, and you need to have a tensile strength, very good tensile strength, because you have two spools which is rotating in the same direction, so that the abrasive wire continuously moves, and the tension between these two spools should be maintained constant, so that the material removal will be uniform. Otherwise it will be a big problem. Okay. For that purpose, if at all I want to maintain the proper tensile nature of the wire, then you should have high tensile strength of this particular material. And synthetic diamond abrasives you can have on this one. Electroplated nickel layer also you can have on that one, so that the bonding will be proper. Okay. You can see also the abrasives and the metal. If you are going to see here, this is a bare material, bare metal, and on top of it you will have abrasive particles and nickel coated layer is also there. Okay. This is about the abrasive wire. Varying the discharge current alters the extent of material removal. As I said, if you are going to increase the current, the melting will takes place and thermal softening of the workpiece takes place. Decrease in the gap width would increase the relative portion and the material removal due to abrasion. If you have very little gap, what will happen? If you have seen the clearly the previous mechanism of the thermal softening and the abrasive particle is protruded out. So normally the abrasion action will takes place more. That means the dominating abrasion action will takes place. MRR is, that means that material removal rate is the consequence of increasing the component of material removal due to two body abrasion. That means that if your current is very less, normally you will have material removal is the consequence of the increase of the component of two body abrasion. That means that your abrasive particle on a wheel is fixed. That means that there is no rotation of your abrasive particle about its axis. That is why it is a two body abrasion in a wire based abrasive machining process. The process can be approximated to wire sawing operation at the lower values of voltage and discharge current. That means that if your current is minimum, at the same time if your voltage is minimum, what will happen? It is dominated by the aberration action. Okay. At the same time, in the previous statement I also said this aberration action will be two body aberration because the abrasive particle is fixed. So, there will be aberration action between workpiece and the abrasive particle in only one position. Okay. If you see the surface morphology of wire, this is the wire. It is a courtesy to Professor Philip Koshi. So, I have taken from the some of the available internet available source. So, I am very thankful to Professor Koshi. And this is the abrasive wire wherein you can see the abrasive particles, diamond particles are there. At the same time, this is coated on top of it, and if you see the same images, so these are the abrasive particles, and the morphology, some of the locations it is uniformly located. This is abrasive, and the nickel coating is there here, and some of the places you will have the agglomerations also. Whenever you have agglomerations, there will be two problems. The material removal will be normally high whenever these agglomeration particles will come into picture. At the same time, if the bonding between two abrasive particles is there, then the bonding will not be proper. So, there will be the delamination of abrasive, some of the abrasive particles will takes place, because if the bonding is between the wire and the coating material and the abrasive particle, it will be always good. If it is the bonding between group of abrasive particles, so the bonding will not be good. So, this abrasive smase goes off. So, whenever you are going to prepare or purchase, you should characterize the wire. Okay. So, this is also the simulated view. Surface morphology of the used wire. Normally, the basic problem with the used wire is the abrasives goes off. Okay. That is why you are not recommended for multiple reuses. So, you can go for few reuses like 1 or 2 exactly if at all you want. So, you can go through the papers of Professor Koshi for more detailed information. So, wire performance decreases rapidly with repeated use. So, if at all you want good performance, you use 1 or 2 or 3 times. If you are going to use multiple times, then the performance will goes down. Okay. If you see the surface morphology between the surfaces, so why I said wire-EDM means if you are going to use the high current, and the normally what will happen is it will dominated by the spark erosion. If you are going to use the high current along with the low voltage, what is happening is here the abrasion action will also takes place, and here abrasion plus spark erosion, both will takes place, because of which material removal will be very high in this area. Okay. Increasing the material removal rate due to abrasion action will you can see in this figure. So, machine surface morphology, normally if you see here wire-EDM surface as well as, so now no lamellar structure. So, abraded particles were subjected to the intense shear. That means that you can see these are the shearing marks of the abrasive particles. At the same time, erosion, spark erosion also. The spark erosion main work is to melt and evaporate, at least to melt, but abrasive particles will remove the material. In the first case, what will happen? There will be only spark erosion. That is why material removal will be very less in the case 1, material removal will be very high in case 2. Okay. So, what is the difference? Here the abrasion plus spark erosion will be in second case, in first case only spark erosion. That is why material removal by abrasion was the first thermally softened by the electrical discharge. That means that first it will be thermally softened by the electric discharge, then it will be removed by the abrasion action. So, summary of the today's class: Introduction to electric discharge machining. We have studied material removal mechanism in electric discharge machining. Electric discharge grinding we have seen, where the only metallic disc will be there. Then we proceeded to electric discharge diamond grinding process, where the abrasive wheel will be there. So, metallic bonding wheel is brazed with diamond particle, or it is clubbed with diamond particle. At the same time, material removal mechanism in electric discharge diamond grinding we have seen, and at last we have seen in the finally we have seen abrasive wire electric discharge grinding process, and the mechanism of the electric discharge diamond grinding and abrasive wire electric discharge grinding both are the same. Only thing is that application wise you may have slightly different. Thank you for your kind attention, and I am very thankful for Professor VK Jain for supporting me in some of the slides. At the same time, I am very thankful for Professor Philip Koshi for his slides that I procured from the internet and other sources. Thank you.